Greetings, Chem 110H. I'd like to go over the Bohr model of the atom. This was proposed in 1913. One of its great successes was in being able to explain for the first time the Rydberg equation for the spectral lines for the emission of the hydrogen atom. However, the Bohr model of the atom has a number of shortcomings. You can read about those in our textbook as well as in a physics textbook. One of the main failings of the Bohr model of the atom is because it's a planetary model, it's completely deterministic. If you give me the initial velocity and position of the electron, at some later point in time, t, I can tell you with absolute certainty where that electron will be. In reality, that's not true. The position of the electron at some later time t is probabilistic, and it's the Schrödinger model of the atom, which we'll teach in class, that gives the proper explanation and probabilistic explanation of the atom. So the Bohr model made a number of assumptions. The first is that angular momentum is quantized. You're already familiar with linear momentum, mass times velocity. Here the mass of the electron, and velocity is a vector quantity. Angular momentum is linear momentum multiplied by r, where r is the separation between the electron that is orbiting the nucleus. We can then look at the equation for quantization of angular momentum. The angular momentum here on the left is equal to n times h bar. H bar is equal to h over 2 pi, and n is a quantum number, the principal quantum number, and n takes on values of 1, 2, 3, and so on. Once we have this equation, it can be rearranged to solve for r as equal to n h bar over mass of the electron times velocity. The second part of the Bohr model is that the inward centripetal force comes about from the Coulombic force of the attraction between the nucleus and the electron. The equation for centripetal force is given here, and the equation for Coulombic force is given here, which is related by this equation over here and is very similar to the Coulombic energy that you saw in class, but divided through by another distance r. This relationship that can then be rearranged to solve for velocity, which is given over here. If we go ahead and calculate the velocity for a hydrogen atom in the ground state where n equals 1, getting r from up here with n equals 1, we get that the velocity is equal to the speed of light divided by 137, or about 1% the speed of light. The third part of the Bohr model of the hydrogen atom is given by the total energy is equal to kinetic energy plus potential energy. Because the speed is less than 1% of the speed of light, we can use non-relativistic equations and give this by 1/2 mv squared, the classical equation for the kinetic energy. And the potential energy is given by the energy for attraction between the nucleus and the electron, which we know from our IMFs for ionic interaction is given by the product of the charges divided by r. And the constant, the proportionality constant here, is 1 over 4 pi epsilon 0, where epsilon 0 is the permittivity of free space. We can then substitute into this equation in place of 1/2 mv squared. We can get 1/2 mv squared from here, multiplied by 1/2, move the r over here, substitute in, add together, and we can obtain this relationship for the total energy. Now that we have these relationships, we can go after the value of r, the radius of the atom. In order to do that, we're going to return here to the first equation, which has r in it. We now have the velocity v from this equation here, and we'll go ahead and multiply that equation by the radius and the mass of the electron. We've done that here. Since we had to bring them in under the radical, we have the mass of the electron squared, and we also have r squared. We can go ahead and solve this for r, which we've done here. While this might look rather complex, what's profound about it is that r is now in terms of physical constants of the universe. In particular, r is a function of the atomic number z, which is an integer, the principal quantum number n, also an integer, e, the charge on an electron, h, Planck's constant, epsilon naught, the permittivity of free space, and m sub e, the mass of the electron. We can then go ahead and calculate what's commonly referred to as the Bohr radius A naught, which is for the hydrogen atom in the ground state. Hydrogen has an atomic number of 1. The ground state has n equals 1. When all of these values are substituted into this equation, we end up with a value of R equal to 0.53 angstroms. So the final thing that Bohr wanted to do, and perhaps the most important, because it had the potential to relate his theory of the hydrogen atom to an experimental measurable, was to ask whether or not he could explain the Rydberg constant for the hydrogen atom. That constant is in terms of the energy equation, so he turned to this expression for the total energy. He substituted in the value for R, which had been solved here. The final expression is shown here, and it can be related to the equation for the Rydberg constant. N squared can be pulled out, Z squared can be pulled out, and one's left with this expression right here for the Rydberg constant of the hydrogen atom. We see that it is in terms of fundamental constants of the universe, the charge on the electron E, mass on the electron m sub E, the permittivity of free space epsilon naught, and Planck's constant h. When these were all substituted in and calculated, Bohr ended up with the correct value for the Rydberg constant of the hydrogen atom. While Bohr's model of the hydrogen atom is impressive in the sense that it's able to come up with the correct value for the Rydberg constant of the hydrogen atom in terms of fundamental constants of the universe, we must remember that the Bohr model is incorrect. It's completely deterministic, and a correct model needs to be probabilistic. We'll see that the Schrödinger model of the atom works not only for the hydrogen atom, but also for multi-electron atoms, and it too is able to come up with the correct value for the Rydberg constant of the hydrogen atom. Thanks for listening.